and the sort of basic ideas that we've got to, is that what we've been doing so far is going through all the basics of the atmosphere, the ocean system, the fundamentals of salinity, radiation, all these things which make up the atmosphere-ocean system. And as I said yesterday, the idea is that this first block up into the modelling is something which is quite factually based. It's based on the idea that you really sort of have to have a grasp of the basic structures that we're dealing with. And that's why it will be examined in a particular way, which will be factually based and will not require nice long essays in which you can wander off the subject and do all sorts of things and repeat yourself and put in introductions and conclusions and gradually fill in time for an exam until we tell you to stop writing. So it is something which you need to sort of get the basic idea behind the first part, really, the first half of the module is to get these basic understandings quite firmly embedded, and that's what we're going to try and assess. The practical that's going along by the side of it, which Kate will come back to next Tuesday, and for next Tuesday I will remind you by email what to bring. But the idea behind that is to sort of bridge the gap between these basic ideas of how the system operates and the reality of how we deal with trying to understand the past, using that to understand the present and into the future. So it's a sort of bridging mechanism of saying this is the actual data we're dealing with. This might be the theory, but the reality is this. And then the last part, the last half, the sort of second half of the module is about how we find out about the past environments and how we can make inferences about that. And we summarise that, or I summarise that, by looking at the IPCC Working Group 1 report on the science of climate change and the whole way in which paleoclimate data are becoming of increasing relevance to understanding that. So that's the sort of the whole totality, if you like, that we're trying to get through, and that's why the structure is the way it is. What I'm going to spend 2 sessions doing, this session today and the session sometime next week, one of the ones, whichever one I said on the thing is next week, is to talk about climate models. I'm not going to go into fantastic detail about climate models and how you work them and the physics and the maths and whatever. That is just not it's relevant, but it's not something which we really can get attuned to. But it's very important that you understand how climate models operate, what the principles are, and in particular how we use the models and how we interpret them for projections into the future. So I've divided what we talk about modelling into 2 parts essentially. The first I'm going to deal with today, which is, if you like, the basics and nuts and bolts of climate models, and how we link what we've talked about with basic processes and observations to developing models that attempt to model the atmosphere, the ocean, and the overall circulation. In the second part, I'm going to look more at the actual way in which these models have been applied, the sort of range of models that there are, and in particular, how we decide on the assumptions that go into the models, which are not basic science, basic physics. So we're going to spend quite a bit of time just looking at the way we decide what's going to happen into the future to drive the models. So the basic idea today is to sort of give you what models are and how they broadly operate, and then I'll look at the application side in part 2. And so this may not slip into 2 nice, neat 2-hour blocks. As soon as we've got to the end of the first block, we'll finish it so that we've got a clear, part 1 is clear, and then part 2 we can discuss as one unit next week. So what I'm going to talk about is scientific models, what models are, and give you some very simple ideas. And first we need to consider what a model is. If I say model to you, I can imagine some of the images that come up, but basically what I've realised over the years is that we tend to use terms like models, and actually you don't really know what I'm talking about, in the sense that it's not something, it's one of those words that we assume is everybody understands where we're talking about. A model is, as I've said earlier, a simplification of reality. And models, although we tend to think about models as really complicated things, because it's a model of the whole Earth system, it's a model of the whole world economic system. It's hugely. Our image of a model is these great big computers grinding on and on. Really. But the reality of those models is that they are very great simplifications of the system which we're talking about. And they rely on simplification and on hypotheses. So we need to understand the system well enough to be able to simplify it into those points which are observable, definable, modelable, but they are structured on hypotheses. These are usually mathematical or expressed mathematically. We're not going into that depth, well, very briefly into that depth. But effectively they are sets of hypotheses, and models are nothing more than sets of hypotheses. Yesterday we discussed the thermohaline circulation, and I made the point that there's just beginning to get some papers saying, don't really believe this operates, don't really believe this works, not sure that this is the way nature works. All the models will have thermohaline circulation firmly embodied in them, but it's a hypothesis. It is a hypothesis of how the Earth system, and it seemed to describe the way the Earth system worked. If over the next 5 years research suggests that it's too gross a simplification, it actually doesn't describe the way the system operates, that hypothesis will have found to be wanting and will be replaced by new hypotheses, new simplifications of the process. And this has happened with models all the time. This is how they evolve. So science, in theory, operates, and this is basic scientific method you'll have before. You have an idea, a hypothesis, which is usually grounded in some observation. So, we're not suddenly flying in from Mars and coming up with a hypothesis about the way the Earth system works. There is some basis to the hypothesis, but we could take thermohaline circulation and overturning a deep water formation. There's a hypothesis that basically that's what drives the Earth system. So we formulate a hypothesis, and then you go out to observe what's going on to see if the observations match the hypothesis. And with the thermohaline circulation, we've got to the point now where, because that hypothesis of areas of deep water formation flowing all around the globe, has been sort of the basic idea, the basic model. What's happened now is that over the last decade in particular, observations have been put in place to see, right, if that's the case, then this is what we should be finding. This is the way water should be moving. This is the way it should. This is the character of the water. And so the hypothesis is we have an overturning circulation, deep water formation drives it. We then go out and make some observations to see. We then get to the crucial stage that if those hypotheses are supported, they might be correct. The hypothesis is still very Kuhnian, very Popper, very Karl Popper, the idea that you keep going on until you can reject. It's never correct, it's never right, you can never prove something, you can only disprove something, but at the moment it sort of still is okay. If the observations don't agree with the hypothesis, you disagree, you've got to reformulate a hypothesis and start again. And so that's applied into the way we build models, because scientific models are essentially a collection of interlinked hypotheses. A hypothesis about how the atmosphere works, a hypothesis about how the ocean works, hypotheses about how they interact. And effectively, a model at any one time is fundamentally a snapshot of our knowledge at that time. And it will change, it will evolve as the testing goes on through time. And we have to accept that if our models don't agree with the observations, then it's our knowledge, assuming that our observations are correct, which is a bit of a minefield on its own, in the sense that you assume that your observations and you've tested all your equipment, etc., and you're assuming they're correct. It's more likely they are going to be correct, rather than the observations are likely to be correct, rather than the knowledge. But the basic knowledge is wrong if the models don't agree with the observations. But we're always getting to a point of to what point do we accept that we don't agree? You know, because it's not a black-white situation. It's often, well, it sort of explains 80% of what's going on. It explains 90% of what's going on. At what point do we actually accept that that's good enough? But the understanding of why our models are wrong improves our understanding of the system. So let's take this observation that we used way back early on. This is a prediction of temperature related to albedo and solar radiation. You've seen this before. So we can predict for any planet the temperature of the planet based on solar radiation input, based on planetary albedo, up on the right there, and the Stefan-Boltzmann constant, which is applicable across, as a constant across all these planets. Basic energy balance model. Very simple, represents two processes. It's two processes, incoming driving solar radiation, the energy that's flying in, albedo, that's the stuff, that's the degree to which reflection from the surface is taking place. So in that simple climate model, we have the Earth, we have sunlight coming into the Earth, we have reflected shortwave radiation, so shortwave radiation coming in, that's our first part of the model. Our albedo of the Earth is the proportion that's reflected. Very simple model. And all that equation is doing is saying this is how the Earth operates. Very straightforward, according to also basic physical laws which we fairly believe in. That warms the planet, and it's the proportion, and a proportion of that absorbed shortwave we can estimate depending on the nature of the albedo, and then we lose the reflected shortwave radiation out. If we apply that model, and again I showed this goes back to the first lecture, what we discover is that Venus lies right over here. The Earth does not lie on the relationship predicted by the model. And we went through that, and clearly the fact that the model doesn't explain